Hello, everyone. Welcome to the Easy Power Thursday webinar series. My name is Jim Chastain. I'm the host for today's session. Before I introduce our guest speaker, as we are in the habit of doing, I want to conduct a couple poll questions to make sure we have a perspective on the audience's attention. Would like to announce a couple housekeeping notes. We will be recording and posting this webinar to our website, and there will be a PDF copy of the slide presentation at the same link. So we make that available, and then all attendees will receive a certificate of attendance that most folks use for ECU credits. So again, welcome very much, and let's kind of get into our poll questions. So the first question is, in your opinion, what lightning protection system concept provides the best lightning protection? Obviously, there's no obligation and no liability, but we would appreciate your participating by giving us your feedback. So if you would please select, and this is becoming more and more of a topic of concern, especially as more sites are located in parts of the world that are more exposed to lightning. So we're trying to get as many people participating as possible. We're about 2/3 of the way to a quorum. If we could get a few more, that would be useful. And so here's how folks have weighed in on this topic. Looks like we have some fairly strong opinions on the subject. And the next question is, which concept is more expensive in your opinion? And obviously our speaker is going to have some information in this regard, so hopefully it'll be valuable as we proceed. We are very fortunate to have our guest speaker join us today, and we're looking forward to the information that he's going to provide. All right, looks like we have a quorum. Here's how people have weighed in on this topic, and obviously we're talking to the right audience. And then the last question is, this is the one that I'm kind of curious about. Which do you think the existing standards adequately cover isolated LPS concerns? Fuzzy pretty much describes my standing. So let's get a few more participating responses. Very good. We appreciate your participation. And it looks like I'm in the majority on this one. All right. So our guest speaker today is a senior engineer with Dane Industries, comes to us from Fort Pierce, Florida. And with that, I'd like to hand the podium over to Stephen Weber. Stephen, you have the baton.
Thank you, Jim. And thank you to Easy Power for this opportunity to share knowledge on this platform. It's really interesting to see the three poll questions and what the people say, that in overall, they think a bonded system is a better lightning protection system, and they expect an isolated system to be more expensive. And then obviously, I share the sentiment that the aspects of isolated lightning protection systems is not really adequately addressed in lightning protection standards. But I'm going to focus on those three aspects, and I'm going to try and discuss how, and hopefully maybe change a few opinions, but also keep that in mind as we move forward through this presentation. So if we look at my presentation outline, first off, I want to discuss a problem statement, and that's basically the problem of an isolated system versus a bonded system, and differences between the two, and before we can look at these type of systems, we first have to understand the characteristics of lightning current. So I want to explain, when we look at the lightning protection system concepts, what specific characteristic of lightning current is addressed by a specific system, or addressed by a specific mechanism that we implement to reduce the risks for that specific characteristic of lightning current. And then we'll dive deeper into the bonded and isolated lightning protection systems and see what does the standard say in terms of definitions and interpretations as they are currently? And it's good that most people say that it's a fuzzy area, because I will tend to show you what or interpret what the standards say on this. And then specifically on the NFPA 780, the term the bonding distance calculations, and of course the requirements that we can find in Annex C, where it's an explanation of bonding principles. And then the same for the IEC 62305 standard, where we have a similar concept called the separation distance. And then how do these calculations actually correspond with each other? Do they actually correspond? And what considerations do I need to take forward after I do these calculations? And then once we've explained the bonded and isolated concepts, what can I do, or what do I need to look for in the risk assessment to determine what system is the best to implement for my specific structure or for my specific system? And they will touch on a few other factors that, we have our risk assessments as they are in the NFPA and in the IEC, and they are quite similar, especially if you look at the complex or the detailed risk assessment that we have in NFPA compared to IEC 62305 Part 2. But also, just thinking logically and practically, when I implement an isolated system, what should I expect from the system and how would it behave? And if I do a bonded system, what other risk factors do I have to take in consideration, not necessarily covered in a risk assessment as it is in the standards? And then a very, very awesome software tool that we started using, and then the XGS Lab software, where we use the frequency domain simulation module, where I would take it a step further and show you if we compare a bonded and an isolated system with each other in terms of what do we expect from current distribution through the lighting protection system and the grounded metal bodies part of the structure. And then this is all very good information, but then if we talk about one of the areas where this is of the highest importance, and that is in classified or explosive atmospheres, where dangerous sparking or flashover or uncontrolled distribution of lightning current is not something that we really want. And they will cover a few things that need to be done if we implement a bonded or an isolated system. And then most important aspect is, once it's implemented, obviously the maintenance and inspection aspect of looking at these systems. So moving on, as I've stated, the NFPA and the IEC published lightning protection standards, and they both show requirements for distance calculations. And the standards also use similar terms when they talk about overhead ground wires or masts, like for instance in the NFPA, where they call it side flash distance, and obviously in the IEC, where it's referred to as separation distance, specifically to evaluate the need for bonding these lightning protection systems. So if it's one thing if we're looking at a very tall building, and we all understand that if you have a tall building, it's hard to maintain a separation distance between lighting protection components and metallic installations in the building or on the building. But in the case of explosive, in the case of tanks that are only up to maximum, 40 feet high or 12 meters high, there's a couple of other things that we can use in our toolbox to derive a requirement for bonding or not bonding, or not to bond. This calculated value of free space, this clearance, is then decisive for what is a bonded or an isolated system. So this is all based on the existence of a very large potential difference, and we'll look at that when we discuss the characteristics of lightning current, that obviously then results in a flashover or dangerous sparking that can occur between components of the lighting protection system and those grounded bodies. And obviously, like I've mentioned, it's a seriously dangerous condition in the presence of explosive atmospheres. So as an introduction, the LPS components that maintain a separation distance from these grounded metal parts, obviously we refer to them as isolated or insulated lighting protection systems. But then we have the concept of where the lighting protection concepts are bonded because they are within the calculated bonding distance that it needs to be bonded back to the grounding system or the grounded metal bodies in order not to cause these dangerous sparking. And that's what we refer to as bonded lightning protection systems. But it's not always that simple. We overlook a few important aspects sometimes when we implement these systems. Like, for instance, if we look at a bonded system, we sometimes overlook the fact that we need to have it places a higher importance on the grounding system, as we have metal parts of the structure that's now going to be subjected to lightning current or partial lightning current injection, and we have to make sure that we have a very solid equipotential bonding scheme for bonding metal pipes, incoming services, and all those things. The next point is sometimes we get confused about the inherent property of tanks being inherently self-protective. And there, again, we have certain requirements like the material thickness and is that adequate, as well as if it's not a sealed metallic tank, but there exists external explosive zones where the charge of the lightning current would cause smelting or sparking, or melting or sparking. And then next, we often make a lot of LPS design mistakes, like, for instance, implementing this bonding distance calculation in the standards incorrectly. And also, when we talk about implementing the system on a structure, we sometimes use the wrong material not tested, not rated, or material of the wrong type of the wrong type, like, for instance, stainless steel compared to copper, and what the temperature rise would be for these materials if they do get subjected to lightning current. Then we overlook the fact that if we have a bonded or a tank system in explosive atmospheres, or even just a natural gas compressor, we have to look at lightning current distribution. If this thing is protected by a lightning protection system, we have to take into consideration the fact that we don't distribute lightning current into these areas with explosive atmospheres. We want to try and get the lightning current separated and get it down to the ground as quickly as possible, and distribute it into the grounding system. And then the same for distribution, lightning current distribution into the sensitive electronic control, and notice also fire prevention equipment, where we don't want the fire prevention equipment to be damaged because of the fact that we are injecting lightning current into places that we did not think it would be a problem. Then obviously that flows into inadequate surge protection measures. And what I also have there is incorrectly implementing these isolated lightning protection components requirements, and then obviously exceeding the product limitations. And then lastly, like I said, we sometimes have a lack of maintenance and inspection. And the consequences, if you just do a recent search, you'll see, I did a search, I think 2 days ago, and I saw damages and we see them all over the world. In this specific case, the first 3 things that I found on Google was, on the 6th of May, on the 11th of May, on the 31st of May, and they're all seem to be a common thing. It's lightning that's sparking tanks, or oil tanks, or tank farms, and that just brings the need back to having conversations and webinars like these, where we can discuss, what is not done correctly here. Are we overseeing something? And that's what I'm trying to discuss with you in this webinar. So, like I said, before we look at the implementation of these 2 different types of systems, let's just quickly discuss the characteristics of lightning current. So, first of all, the first most important thing is obviously the peak value of the lightning current. So this high magnitude of current is what actually causes this excessive voltage drop across these conductive parts. It's simple Ohm's law. You have a very large potential difference that can then exist between something that is bonded and something that's not 2 points that's not bonded together. And because of this high peak value or this high magnitude of current and high voltage, resulting voltage, we can get that flashover. So that's the first thing that's a characteristic of lightning that is very important when we think about these two types of systems. The next is the steepness of the lightning current. Now, the steepness of the current rise is what causes the electromagnetic induction of very large voltages in these conductive loops that we have in the vicinity of the lightning protection components. And that is where we, like I've mentioned before, where we've come to where the standards have come to the concepts of calculating separation distances that needed to be maintained in order to make sure that these conductive loops are not so close to LPS components that the induced voltages are so that there will be a dangerous spark or a uncontrolled flashover. So you can see both of these characteristics already. You can already think about how they are relevant for a lightning protection system, be it bonded or isolated. Then a very important aspect or characteristic when we consider something like explosive areas is the charge. The charge of the lightning current is decisive for that energy conversion that we get at the exact point where the strike terminates. And that is basically where we can cause melting or puncture or sparks or a very high temperature gradient where we could actually exceed auto-ignition temperatures or even exceed the temperature or the auto-ignition temperature because of the inner linings, inner insulation reaching a temperature that it shouldn't. So here, very important, the standards mention what would be the minimum thickness that these tanks or lightning protection systems need to be able to withstand this charge associated with lightning current. If you're talking about natural or inherent protection, we have very similar thicknesses in the NFPA and the IEC, both referring to about 4.8 millimeters for the NFPA and 5 millimeters for explosive tanks, as it's said in Annex D of IEC 62305. There's some examples, exactly what you can see, that puncture, that melting, that sparks that we can see, and that's all based on this characteristic called the charge of the lightning current. Then the specific energy that the system is subjected to is what makes an excessive temperature rise in the conductors carrying this lightning impulse currents. So this is very important to understand, that you have a system that you are designing to be able to withstand a certain maximum lightning current. And you have to design it so that the current that's going to flow through this material is not going to make the material temperature rise so high that it would obviously exceed the ignition temperatures of what atmosphere is surrounding the structure, and therefore result in a problem, flashover or a fire or an explosion. So you can now see that these 4 characteristics that I've mentioned, all 4 is really important to understand and to take into consideration when you're looking at the type of structure that you are protecting. And we'll discuss it further, and when I'm done, you'll understand what lightning protection system addresses what characteristic and how these systems are designed moving forward. So, like I said, we'll cover the standards definitions and interpretations. And what I've put on this slide is the NFPA 780 standard and the IEC standard. And then on the right is a pillar that we always use to explain all of the 5 pillars of a structure with all of the 5 pillars of lightning protection. So we obviously have the 3 main components: the air termination, the down conductor, and the earth termination system, primarily responsible for intercepting, conducting, and distributing the lightning current away. Then there's the 2 other pillars that we use to address the effects of the lightning current, or like I've just said, the effects of the characteristics that we expect from the lightning current. Like I say there, the separation distance, a very important pillar to address 2 or maybe 3 of the characteristics that we just mentioned, and then the lightning equipotential bonding aspect, also addressing 2, 3, or maybe all of the characteristics that we've just explained. So see how important those two pillars are. So what is the standard definition? How does the standard interpret these systems? So the requirement for equipotential bonding is, like I said, derived from this steepness of the lightning current rise that electromagnetically induces these large voltages. And there then exists, like I said, the sparking and these additional current paths. Now, for structures exceeding certain height limits, like 60 feet, additional bonding to equalize these potentials becomes very important, as it gets harder to maintain this separation distance between the lightning protection system and the grounding media. And as you can see, as I show here, that as the length in the graph on the right, as the length of the down conductor becomes longer and longer and longer, we get this linear relationship where the separation distance increases linearly up to a point where it just becomes impossible or highly impractical to maintain this separation distance from systems outside of the building as well as systems inside of the building. Now, the NFPA 780, as it says in its Annexure C, an explanation of bonding principles, it says there that the major concern in the protection of a building is this occurrence of this potential difference between the components of the LPS and this other grounded metal bodies. And it is necessary to equalize these potentials by bonding the grounded metal bodies to the lightning protection system. And this is common for us. This we see everywhere. This is what we obviously would refer to as a bonded lightning protection system. And I agree. And in a lot of the cases, this is the system that we need to implement because of practical problems, practical challenges. And instead of having this uncontrolled or dangerous sparking, it's better to bond the system together. Now, where a structure can be designed, and the IEC further explains in this section, that where a structure can be designed to isolate the grounded systems from the lightning protection components, this should be considered. This is achieved by maintaining the separation distance between these components beyond the bonding distance requirements for building grounded systems above grade. And now that talks back into an isolated lightning protection system. So in other words, as far as you can design a system to keep the lightning separate and isolated, you should do it. You're reducing a lot of other associated lightning hazards. And in saying this, it further says that the isolating lightning protection system elements to provide separation distance from grounded metal bodies, or to increase the number of down conductors to shorten this required bonding distance, are options that can be used to overcome difficult installation problems for certain structures. So what it actually says is that for certain structures, existing or new structures, it's not always easy to bond all of these metallic bodies together. And you can address this by increasing your number of down conductors. In other words, disperse the lightning current even further so that you have a smaller bonding distance calculation, or you can try your best to at least provide separation for certain parts if you can't do it for all of them. And then the IEC interprets it exactly the same way. It says that an isolated external lightning protection system should be used when the flow of the lightning current into bonded internal conductive parts may cause damage to the structure or its contents. So see how both of these say the same thing, but they say it differently. The first one in the NFPA says that they say the most important aspect is to make sure that you don't have this dangerous sparking, this potential difference between components of the lightning protection system and grounded bodies. While the IEC says you should use an isolated system not only then, but also when the flow of the lightning current into these bonded internal conductive parts may cause damage to the structure or its contents. And this is further when remember this when we talk about the risk assessment in a few minutes. The use of an isolated lightning protection may be convenient where it is predicted that changes in the structure may require modifications to the LPS, as a note. And then lastly, the very last sentence, if an isolated LPS it can be achieved by either air termination rods or masts to achieve this separation distance, and it can even be with overhead wires or some other type of insulated conductors, which we'll always also cover. But don't just always think of an isolated lightning protection system as a few masts that need to be installed around the building. It could be done by designing it with this bonding distance requirement in mind and making sure that you comply with it. And then now focusing on the NFPA 780, there's quite a few sections in chapter 4, the general requirements, where sections 414, 415 talks about this common bonding and potential equalization, but then part 16 talks about the bonding of these metal bodies. And this is where you'll find a formula where it says that grounded metal bodies that can maintain the separation distance away from the lightning protection components that is greater than this bonding distance that we can calculate with these formulas, we can consider as being isolated. And there's your formula. Where your calculated bonding distance is equal to the vertical distance between that bond and the nearest interconnections. It takes into consideration the material, and it takes into consideration the amount of down conductors that the system sees. The same with the IEC. This is a similar concept where you have a few other factors, but it also takes into consideration the material that you are working with. It takes into consideration how the current would flow. So in other words, this directly has to do with the amount of down conductors. So because that's the KC factor, how the current distributes. And then that value H that you saw for NFPA formula would be the same, similar than the distance L, where you're calculating that length down to an equipotential bonding point. So just to further simplify this concept for you further is to see it as a little building like this, where at the point S, I need to calculate that separation distance that I need to maintain. And this could be on the outside of the building, it could be on the inside of the building. And then I can use this KC factor for the current that I expect flowing down here because based on the amount of down conductors, the material factor, and the length. And I could calculate that point that I have, that separation distance that I need to maintain at that point. And now, obviously, as I go down the building, my length L becomes less and less and less and less. My KC would probably stay constant, or there might be slight variations if there's additional paths here. But as I move down, L becomes smaller, and as L comes smaller, I have a smaller separation distance that I need to worry about coming down the building. So see why for tall buildings it becomes very impractical to try and maintain the separation distance. Graphically, visually, you could see what is meant with this, where just as a simple example, I have the lighting protection system on the roof, and that's basically that separation distance that I'm referring to. And by maintaining this, I'm not bonding this PV structure to the lighting protection system. I'm not bonding it because I do not expect any one of the lightning current characteristics, be it the steepness, resulting in electromagnetic induction, or be it the peak current, whatever the characteristic, I don't expect it to result in an uncontrolled spark or an uncontrolled flash over to that grounded metal body, because of the fact that I am maintaining this separation distance. And doing this, I now make sure if I do get a lightning strike, I have lightning current that will distribute amongst the lightning protection components and find its way down to the grounding system, and therefore not really injecting partial lightning current into the PV panels. So I'm addressing a hazard that would not exist. That does not exist. That would not exist for an isolated system. But should I not be able to maintain this separation distance, I'm eliminating one hazard, which is that spark over that would exist, by bonding it. But remember now, there will be some partial lightning current that I will be injecting into this grounding conductor that grounds this metal body, providing an additional path for lightning current moving down. Just a few more samples. I think by now you understand the concept of having a separation distance between the two components. The same there, where you have your lightning protection system that has to cross over something that you don't want to have uncontrolled flash over in, and you provide that separation distance in that type of way. Now, we realized that these two calculations actually have a lot to do with a lot in common, and they are quite similar in the case of an IEC Class 3 lightning protection system. So the NFPA, we all know, has a rolling sphere radius of 150 feet. And this just talks back to the fact that an IEC Class 3 lightning protection system has a radius of this, uses the sphere of the same radius. And if you do a comparison between these two bonding calculations, you would see that you get quite similar results in this specific case, where the two would result in the same value, or the same approach and the same value. But like I say here in this last paragraph, the NFPA, like I said, is primarily focused on this equipotential bonding between all metal structures through the facility. And we saw that the IEC again is focused on the fact that they don't want you to inject lightning current into parts of the structure that would result in further risks. So the unfortunate side effect of bonding a system is that it can have damage to unintended victims, like rooftop solar, chillers, and radio equipment that are now injected by lightning energy or insufficiently separated from main conductors. Now, what I did not mention here was this middle part, where one other difference is that the IEC would scale this separation distance calculation based on the severity of the lightning protection system class. Now, like I said before, when you install these lighting systems, you need to make sure that you are designing a system that can maintain or that can handle certain lightning current. And again, here is where you would see that the IEC system would scale its separation distance calculation based on the severity, or based on the lightning protection level, which is the severity of the lightning current that can be expected. So that being said, we now understand isolated, bonded. So what a system is best? Is a bonded or isolated lightning protection the best option for a specific structure? What are the highest calculated risk components? What are your sources of damage that you consider for the structure? So will the bonding of the lightning protection system to rooftop equipment or metal bodies of the structure, and that injection of partial lightning current into a structure, result in higher probabilities of loss of economic value or the risk of loss of human life? And here I would say, think of things like a hospital, a school, a public building, perhaps data centers. And that's very important these days as well, with everything being digitalized. Think about explosive atmosphere. Yes, it's one thing now that I am bonding and I am equalizing potential. But now think of it in a different way in implementing this system, in terms of, is it acceptable for me to inject partial lightning current into these structures? Or, like I say here, can this risk be controlled by additional internal bonding or grounding or SPDs? Yes. How? What do I need to implement? If you could capture the lightning current and keep it isolated, separated from the structure or building and its services, and get it dispersed into the ground safely without ever touching the structure, like it never happened, wouldn't that be lightning protection? Wouldn't that be the best lightning protection? Now, we look at high value assets like lightning masts around substations, NASA launch complexes, biogas plant digesters. We see them often. It's all isolated lightning protection concepts. Now, wouldn't an isolated lightning protection system, in your opinion, provide better lightning protection? So technological advancements and obviously limitations that we have with buildings, starting to make it easier for us to try and implement these isolated lightning protection systems. It's not just the fact that you have to use an insulated or an isolated lightning protection component. It's just implementing the system in the right way, in calculating the bonding distance values, the separation distance values, and attempting to maintain those separation distance and stay away from those from those metal bodies. So to move this conversation forward, if I look at an example for an explosive atmosphere, I have a bonded lightning protection system on the top here with a natural gas compressor within the structure. And all of those always have an exhaust gas stack. So this could be we see this everywhere these days. That a bonded lightning protection system would have a direct connection bonding this exhaust gas stack. And you have to understand that lightning current would not just distribute as you want it to down the down conductors to the grounding system. Some of it will distribute down the exhaust gas stack. And with that, we have magnetic fields that would induce voltages into these conductive loops that we've just explained. And if your equipotential bonding principle down here is not adequate, or your surge protection measures that you have for this equipment is not adequate, or even your grounding system has faults in it, or is not adequate, you are injecting a lightning hazard that would result in further problems. Now, the same scenario, the same application, if I can have an isolated lightning protection system and calculate this bonding distance, make sure that I stay away from it, keep that separation distance, not bond it back, I will have lightning current not distributed within this EX zone 1 down here. And I'm not saying that it places a less importance on surge protection, because we still have lightning current flowing to the grounding system externally, and we will still have a ground potential rise on everything that bonded. But at least we're working with, we have the opportunity of distributing lightning current into the soil and having to work with potential differences down here. We don't have to worry about the electromagnetic induction that we see for lightning current flowing down, trying to find a different way to ground. And we don't have to worry about clearances and insulation failures as we would have to in the previous scenario. So taking this further, like I've said, with the XGSA frequency domain module, we can compare that this current distribution concept that I'm talking about for a bonded and an isolated lightning protection system. So what you see here is exactly the same scenario. I have a building and the air conditioning is bonded back to, or there might be terminals, whatever the case may be, on the air conditioning, and it's grounded and bonded. Everything's grounded down here to the main or the master earth bar, and I'm injecting in the case of a bonded system, I'm injecting this lightning current to try and find a way, and it will find a way back to these grounded points. Now, if I take a system like that and I simulate and I model it in our software, and I go ahead and I inject a lightning current based on the first negative stroke, which is about 90% of the strokes that we receive, at an equivalent frequency of 250 kilohertz. And as you can see here, we have this equivalent frequency that resembles the same rise that we would see if it was a lightning transient. And we simulate the system this way. And I'll get to results in a minute. And then I just want to mention that the same is done for an isolated system, where we maintain the separation distance. Lightning current is injected and flows on the outside of the building and not on the inside. And then at ground level, the lightning protection grounding is bonded. It's the same grounding system, one earth, and it's all bonded back together. And simulating this type of system that you can see here, there it's isolated and away. And the previous scenario, it is on the structure. The structure is part of the AC conditioner is bonded. Now, if we look at the simulation results, a bonded system would receive the lightning strike on that terminal, the way in which we would implement it. Now, notice that this outside conductors is the conductors of the lightning protection system on the roof. These are the down conductors. And you'll notice that they're all, I would say, a nice little a nice blue color, nice sea blue color. And just see on your legend where that puts it roughly. Now, look at the grounding bond, indirect grounding, or the metal body's grounding bond that goes into the structure. And you've got all these metal ducts, like I showed in the previous picture, and it all goes down to this main earth bus bar. Now see the amount of current. You can even see the color, orange there's some green, and they all diverge and come back to this main earth bus bar where it gets red again. So if you look at the difference in colors, there's quite a portion of lightning current that distributes into the structure. And that's why I said injecting this lightning current into the structure, that is in the risk assessment of the structure, be it a school, a hospital, a library. This is something that needs to be considered. Now, if I have computers, if I'm a data center and I have equipment bonded back to this main earth bus bar, you can see that even with a nice grounding grid and nice earth rods according to NEC, I still get a lot of current distribution coming to this main earth bus bar. And see the importance this now places on having adequate surge protection measures, making sure that metallic piping and everything is bonded correctly. Now, the simulation for an isolated lightning protection system, I'm maintaining that distance. I won't get that uncontrolled flashover. See how much current stays in the lightning protection system. Where we had these down conductors blue, we now have them green. And that just, and in the case of the closest down conductor, which is the path, the most direct path, you'd see them as being orange. So most of the lightning current would distribute through the lightning protection system the way we want it and go to the grounding system. While some of it will still flow well, basically you'll see current distribution through the grounding system and then back up, as you would see as you would see over here. But now, in this case, you would see that there's a significant difference in the amount of lightning current that we can simulate at the location of the main earth bus bar and at the location of other grounding points to the ducts and if there was a computer or a data center or whatever the case, a closure or whatever the case may be, there's not a lot of current distribution flowing in this on the inside. So yes, there's still, if I run a ground potential rise analysis, I would still see that there's a massive ground potential rise because of the ohmic value of the grounding system. Then yes, I understand. Then we would place lightning protection or surge protection measures to address those potential differences and to equipotentially bond the electrical system that way. But just comparing the distributed lightning current that we can expect at this location, there's a big difference. Yeah, the same simulations. I just thought that if we wanted to see it at a different angle, however, I do see that I've lost a little bit of quality. But if you look at this in different angles, you could notice that with a bonded system, you can clearly see that there's a flicker of orange and a flicker of green, and not the nice blue flicker that we would see. There's some red flicker that we see there for the lightning current and green on the down conductors. But on the internals, we can all see that's just blue flickers. That's low values that we expect, but that's all because of the distribution of some current in the ground and then others that would flow back into the system through this ground connection. But at least we had the opportunity to now distribute it into the soil before distributing it into our building. Let's talk about an explosive area. So you come across a lot of clients that do talk to you about the inherently self-protecting property, where you have to ask the question, is a direct lightning strike to the tank structure acceptable? Have you thought of things like melting and spraying effects on the point of strikes? Have you thought about things like the temperature rise that you will see on the inner surface? And then more importantly, thickness requirements. Is your tank constant or electrically continuous and constantly has a thickness of 5 millimeters of steel, so that if lightning were to strike it, it would be able to withstand that charge? What if your tank is surrounded by an explosive atmosphere? Do you still consider inherently protection for the tank? The strike termination point now is within this explosive area. So if there's just a slight spray or a slight spark, is that something that you would accept? So what about using the tank structure as a natural down conductor? Yes, it might comply with the thickness requirement, but then, is there still a risk of any ignition of possible explosive atmospheres? What if I have metal conduits or instrumentation, and my equipotential bonding practice is not as well as I think it is, or I've not inspected it for 12 months. How do I still know after a year or two that everything is still adequately bonded? That's just the risk that you have to discuss, you have to think about. The specific application for explosive atmospheres, like I said, was taken into consideration other points as well. Like if I do have light and protection components, how do I make sure that I have constant tensioning on these fixings? Do I use clamps that have spring washers in them? How do I make sure that there's a constant, do I have a maintenance program where I go and inspect the torque and retorque every now and then? How do I make sure my component test ratings are in place? And then, like I said, where do I place my strike termination devices? Some of these tanks, it's hard to provide an external strike termination device. If I do place one, the NFPA standards and the IEC standards actually recommend to have these strike termination devices outside of the explosive atmospheres. So something that you need to consider. The material of the components, in other words, copper versus stainless steel. And we know stainless steel has a much higher delta Kelvin temperature rise coefficient that it would have than compared to copper. So make sure you have the right material for that temperature rise. And then your down conductor routing, both standards say try and route it as far as possible outside of the explosive atmospheres, but not always possible. So like I said, these bonded systems, have a very high importance on the grounding and the bonding for the lightning current to safely pass through the tank or steel structure to ground. And this high current can also easily spark over small gaps, like I said, with something that's poorly grounded, maybe a lighting circuit, maybe a metallic conduit that's not properly grounded. Most recently, consider tank inspection covers, a unbonded metal closure, a metal cover. Could that be a risk? What about walkways? We saw that in that explosive picture, they always have walkways. Do we need to make other considerations for that? And then what about the grounding system? Is a simple earth rod enough? Do I need to bond these tanks together to try and create more paths? Do I have to have a ring electrode? That's all important things when we have to implement a bonded system. Very high importance on these type of things. And it's not even mentioned here, but surge protection devices as well. And like I said, surge protection devices, a very important role when it comes back to the principle of equipotential bonding, where I need to bond everything, make sure everything, this is right next to the tank, make sure everything is equipotentially bonded together. Now, this is a very nice concept, a very nice equipotential bonding bar. I can easily see everything. It's open for maintenance and inspection, and I can make sure that everything is properly bonded. And then the grounding system, strike to this tank, and there's not adequate, grounding measures on the tank next door, or, you have soil resistivity that is significantly high. You have to make sure that you have a grounding scheme that is in place, that is sufficient to be able to distribute and make sure that everything is safe for excessive potentials in an explosive area. And then an isolated light and protection system can also be implemented by installing these complete mass systems. And we've done it before, where you have these poles and you install these light and protection system, or these strike termination devices on these high poles, and that provides a certain coverage over the tank. But then also, you can achieve isolated light and protection systems by using other components that, as I mentioned here, are starting to move and being considered by the standards committees and the standards, the people in standards circles, where we're starting to accept and validate some of the testing specifications to be able to achieve isolation through standoffs, through specialized high voltage insulated conductors, and then just basically achieve isolated lightning protection systems by following the principles as they are for lightning protection systems currently. And yeah, like I mentioned, you can get these systems to give you a comparable equivalent separation distance that you would have had in free air to install it onto a tank and achieve that same value or that same separation distance. Like in the case here, where you have an EX zone or a vent, and you have your isolated system, even though it's bonded, it's mounted properly, and it runs through the explosive area atmosphere. And in the meantime, it still keeps everything isolated. So in other words, having a system like this implemented on a biogas facility where you now protect this structure against a lightning strike, and it's all isolated, lightning current would not flow in this explosive atmosphere, in this explosive structures, and it would flow to the grounding system. And like I said, does this look familiar? This sure does to me. And we have looked at a couple of these type of tank battery configurations in the past few months, and how we can develop these type of isolated systems to try and make sure that we distribute lightning current and not have partial lightning current distributed to points of equipotential bonding that might fail, might not be maintained, or whatever the case may be. And then, like I say, the standards, I think this is my last slide, Jim, that the standards say here that, we need to make sure that you have a maintenance and inspection plan. And B actually says you should develop this yourself and make sure that you have an appropriate periodic inspection. Yeah, so that is my presentation. And
very, very informative. Stephen, I really appreciate it. We had a couple of questions coming in, pretty much the same topic, and that is, when the substation is constructed of concrete, does that mean you by default need to have an isolated system?
Yes, well, remember with substations, we have standards that I've not addressed here. We have IEEE standards that you need to comply with substations. But yes, if you look at a structure, any concrete structure, it might be even underground tanks, that's underground. If you have a structure that you are doing an evaluation for, and you see that I don't really want lightning current to flow or be injected into the reinforcing of this structure, or I don't want the risk that it could flash over to the reinforcing of the structure, or it's concrete and the thickness of the concrete is not sufficient, that there might be a flash even through the concrete, because that happens, to the internal conductive paths. So yes, and I stand by what I said, that if obviously the best lightning protection system that we can have is to capture lightning, distribute it to grounding systems, and not inject it into any other place that we did not want to.
Well, it looks like we're about out of time. We really do appreciate the presentation, and we will notify everyone when we have the video ready to put on the website. Stephen, thank you very much again. Hope everyone has a good day.
Thank you, Jim. Have a nice day.